This recording will cover circular motion and rotation. We're going to go through basically our rotational variables, and then we're going to talk about torque and rotational statistics. We will talk about uniform circular motion, although I talked about it a little bit up here with Newton's laws. But we'll talk about that one more time. And we're talking about angular momentum and its conservation. So, this is chapter 10. And this is a good job of defining your angular variables. We've got angular position, which is the position as an angle theta between a reference line attached to it. So the angular displacement is how far that position changes. Again, displacement is a vector, so you only care about where you started and where you ended, not necessarily about the path taken to get there. Instantaneous angular speed is omega. It's the rate of change of the displacement, or d theta dt. Instantaneous angular acceleration is going to be the rate of change of the angular velocity. Again, d omega dt. For the most part, this angular acceleration is just going to result in speeding up or slowing down of rotation. To change the direction of a point on that circle, like to cause it to rotate at all, you have a centripetal acceleration as well. And we have a definition of that centripetal acceleration in terms of omega. So centripetal acceleration can be v squared over r or omega squared r. But this alpha is really kind of, well, theta, omega, and alpha are all parallels of x, v, and tangential acceleration. This is a really important concept when talking about rotational stuff. Just one second. When a rigid object rotates about a fixed axis, every part of the object has the same angular speed and the same angular acceleration. They may have different linear variables, but they will have the same angular variables. All right.
Can I like this?
I need you to leave me alone for just a second, okay?
Can I just do this?
Sure. Just do it quietly, okay?
Okay.
Okay.
Pink bunny. Pink bunny something.
Okay, so torque. So torque is the rotational analog of force. A net torque that is acting on a system will create a change of rotational motion, just like a net force acting on a system will create a change of linear motion. But torque is defined as force times a distance from an axis of rotation, and those need to be perpendicular to each other. Sometimes this distance is also called the moment arm as well. And the moment of inertia of a system is kind of be analogous to what you would use for mass for linear stuff. You would use moment of inertia for rotational motion to describe rotational variables in rotational motion. The moment of inertia is going to define not only the mass of that object, but also how that mass is distributed. If you have all that mass distributed at the center, like near the axis of rotation, then you have a low moment of inertia. But if you have the mass distributed out near the edge of that, like far away from that axis of rotation, then this moment of inertia term will be larger. It'll be harder to change the rotational motion. Okay, so there is a relationship between each of the linear variables and our rotational variables that we just defined. And they're all to say S, which is our linear variable, our x, is equal to the radius times theta. And again, velocity is equal to the radius times omega. So a point that is 2 meters away from the axis of rotation, excuse me, that is rotating at a rate of 3 radians per second, would have a linear velocity, a tangential velocity of 6 meters per second. And the same thing applies to this, tangential acceleration. Again, this does not have anything to do with centripetal acceleration. We have another form of energy associated with rotational motion that's called rotational kinetic energy. Linear kinetic energy was 1/2 mv squared. Rotational kinetic energy is 1/2 I omega squared. I'm just going to kind of plug that in for conservation of mechanical energy, especially when something is rolling down a hill and, well, if it's rolling down a hill. The integral form of moment of inertia is this one's really important. R squared dm. Basically, it was 1/2 mv squared, or sorry, mr squared, but it's that r squared dm, and you do need to be able to work some moment of inertia problems with that, and we did a fair amount of that when we did it. And then again, the rate at which work is done is going to be power. Power, the linear version was that it was average force, or force times average velocity. This is going to be torque times average angular velocity. Work will result in a change of kinetic energy. Again, that assumes that the Earth is not part of this system. Robin, don't do that. But this is the same work energy theorem, but now in terms of rotational kinetic energy. And total kinetic energy, be careful, it's going to include, for something that's rolling without slipping, is the rotational kinetic energy of the whole object plus the translational kinetic energy of its center of mass. And there are kinematic equations in rotational variable form. Robin, do not do that. An object under a net torque will experience a change of angular motion. That's defined here. The sum of the torques is equal to the moment of inertia times the angular acceleration. It's kind of the same thing as F equals ma, but again, now it's in rotational variables. Net torque is equal to I alpha. I think that's it for most of rotational motion. I'm going to get, there was one more thing in there. Oh, uniform circular motion. Let me go back and do that one. And statics I will do in just a second. So I'll get these first two in just a second.